going to seem kind of like, what is the point of even talking about that? But that's why we're going to do it at first, just to get some ideas down, and then when we go to actually do the operations, I'll say, remember we just talked about that, and this is why we talked about it. So to begin, we're just going to start with the concept of matrices that are equal to each other. And this will be helpful, for example, if we were setting up an equation of matrices, and maybe something was missing, it had a variable, and we wanted to solve it. Then we would want to talk about, well, what does it even mean for matrices to be equal? Because if we had a matrix equation with the equal bar, we would want things that were equal on either side. And these two circumstances must be met before we can say, that two matrices are equal. Hannah, would you read me the first condition, please? Okay, thank you. What do we mean when we say that matrices have to be the same size? What specifically are we talking about? Not variables. The number of rows and columns, okay? The rows have to be the same number or amount. The columns have to be the same number and amount. Krista, read the second one for me, please. All right, thank you. So they have to be the same size, and then corresponding entries must be equal. What do you think this word corresponding is trying to tell us if we're talking about two matrices? What would corresponding entries be? The same on both sides. Okay, I like where you're going with that. Can you be more specific? The same value on both sides. That would be equal, right? The same number. So when we say they have to be equal, we're talking about their values, and that will be true. But what do you think corresponding entries means? That doesn't really have anything to do with their value. That has to do with their placement. What do you think corresponding entries would mean? Same things in the columns and the rows, right? So if you have two matrices, if I were to say, if I had these two matrices, in this second matrix, which number corresponds to 1 here? 4, okay. Which number in the first matrix corresponds to 6 here? 3, okay. And this is going to be a very important concept. When we start adding, we can only add corresponding values, and so that needs to be a concept like you got that. When I say you're only adding corresponding values, your brain needs to go, oh, okay, they have to be in the exact same position in the matrix, all right? This stuff right here is the very mathy way of writing this stuff right here that's in words. And in fact, if you go to college and you study math or engineering or whatever, this is the way stuff is written in textbooks. This. Not these words that make it easier to understand, but this math notation. This is basically saying matrix A is equal to matrix B if lowercase a sub ij equals lowercase b sub ij. What does this notation mean from the other day when we were introduced to matrices? Lowercase a means we're talking about what? Entries, right, in the matrix. And what does that I and that j represent? Remember? Rows and columns. The I is rows and the j is columns. So this is saying if you have these two matrices, we know these are matrices because you name them with a capital letter. Then the entry with the exact same position, the row is the same, the column is the same. These are equal only if the entries are equal for all I and j, for every single combination of row and column you can come up with. Now there's more of these in our notes. I'm not going to have you ponder that every single time we encounter it in our notes, but it's good for you to see it every once in a while. Yes, sir. The variable version? Yeah, yeah. So what's good about writing something like this in this mathy way, even though you might feel like that's just going way over your head, is that once your brain starts working like this is a very precise, exact, accurate way of writing something with no confusion. And that's what's good about using mathematical notation. I won't ask you to do that again later anymore today. All right, so we have here two matrices. And all we want to do is determine if the following statement, by statement it means this thing. That equal sign makes it a statement. This is equal to that. We want to know if it's true, false, or conditional. By the way, it's not conditional. I'll talk about this in just a second. We're going to talk about it on the next one. So really, I'm just asking you to figure out, do you think that this statement, that left matrix equals the right matrix, is true or false? And explain why or why not. Who thinks it's true? Okay. And who thinks it's false? Okay. Of the people who voted, that was about half and half. And then the rest of the half of the class didn't vote. So here are the two things. So first of all, the first thing we have to check for, are they the same size? Okay, so that checks. So the next thing we know are the corresponding entries equal. So let's do that a little bit at a time. So here's 3. What corresponds to that position over here? 1. Are those equal? Is this a true statement then? It's false. It's false because, what kind of wording could you use here as a justification? It's false because, what are you saying, Hannah? Perfect. Corresponding entries aren't equal. If you give me something that's not that much like that math vocabulary, like if you say the stuff in the same spots isn't equal, I'll take that. But I really like corresponding entries aren't equal. So those two matrices aren't equal. They're the same size, but their values are different. Does anybody need this up anymore? So then we have this thing. My screen has a B right here. I fixed it on your notes. You should just have an A. I just want the A. Determine if the following statement is true, false, or conditional. I'm just going to go straight tell you this is conditional because I kind of want to use this example as a way of defining what this means. Just in general, when you use the word conditional, what are you implying? Everyone? Something might be true if a certain condition is met first, right? And that's the exact same way we're using it here. This would be a true statement if a certain condition is met first. Any guesses what that condition might be? Jasmine? If A equals 1. Because what do you notice about every other entry, corresponding entry? They're the same. So this is conditional. So make a note somewhere, because you might forget later, like when you go to do your homework, and it's like, I don't remember what she meant about conditional. Basically, if there's variables there, there's variables. So the answer is conditional because variables, or there are variables. This is a math symbol for there exists. Can I leave that there, or do you want the words? Okay. There exists variables. Find the value of A that would make the equation true. You said A equals 1. So A equals 1 is the condition which, once met, makes the statement true. And that's why it's a conditional statement. If that A was already a 1, if this wasn't here and I had 1, what would you be saying for your answer? True. All right. Anybody need that up anymore? The point of these things are to get your mind working on a few concepts. Sizes of matrices, corresponding entries. All right. Write your answer for that one and write down an explanation for that one as well. Determine if that is true, false, or conditional, and explain why. did you say? Yeah, that's true. So let's look at the requirements. They must be the same size. Okay, good. Now this was true though, right? Yeah, really, really fast. Okay. It is false. Right. Because that first, it's true that the entries are all the same, but it's not true that they're the same size. Eli, what'd you put, please? False. And your reason? Okay. Like the same size. Thank you. The rows and columns aren't. What'd you notice about the entries? They're the same values. They're not corresponding entries, though, because the sizes are different. So it's false because sizes are different. What are some other, we have two other words we've been using that we could have instead of size. Do you remember one of them? Dimensions, what else? Starts with an O. And then an R. Octagon, no, absolutely not. Order, order. Order, you could call it the order, the size, the dimensions. Okay, either of those are all kind of meaning the same thing. All right. So now, having laid all that groundwork, okay, now we're going to talk about how to add or subtract matrices. I am recording, right? Okay. Casey, read this first thing for me. What needs to happen before I can add or subtract? What needs to happen first?
Both matrices must be the same size.
All right, thank you. So if before we can even add or subtract some matrices, we have to be sure that they're the same size. So their dimensions have to be the same. Okay, they have the exact same number of rows, the exact same number of columns. It does not need to be true that anything inside there is equal. It can have all different numbers on the inside. Okay, so we're not talking about equal matrices here. We're just talking about matrices with the same size. To add or subtract matrices, you just add or subtract their what's, class? Corresponding entries. Okay. So two things have to happen to be able to add. They have to have the same dimensions, and then once that requirement is met, then you can add and subtract. And what you do is you just take their corresponding entries and you add them. Okay. So like if you have two matrices, top left plus top left number gives you the top left in your answer. Top middle plus top middle gives you top middle in your answer matrix. All right. And it doesn't matter if you didn't follow that. I'm going to show you with my hands in the air, like I just do not care. Okay, so here we go. We have these three matrices. We're going to do these three example problems. Okay. What is the, before you do an ounce of math, what are you checking first? Some of you aren't doing an ounce of math anyway. You're checking size and order, right? Okay. So for A and C, check the size first. What do you conclude after you check their sizes? What, Emily? What do you think? They're not the same. So what does that mean? They're not the same, so what? I can't do what? I can't add them, right? So A is not applicable. Okay, not applicable because different sizes. What would happen if I tried to, if I have two matrices and adding means you add their corresponding entries, and I try to add two that don't have the same size, what problem would I run into? If they were different sizes and I'm trying to add corresponding entries, what problem would I run into? Do you think? Okay, I said, in this case, so for example, in this case, A and C have different sizes, right? But I told you that to add, you have to add corresponding entries. Like you would have to add upper left to upper left. What problem would I run into if I wasn't paying attention and I tried adding A and C? I would have extra numbers that didn't match anywhere else, right? And so, okay. So that's why the dimensions have to be exactly the same. B, I want to do matrix B minus matrix A. Check the dimensions and tell me if I can even do that math. Yes. Okay, it's 2 by 3s. They both are. I need you to understand something, though. The order matters. If I need matrix B minus matrix A, bless you, I'm doing these numbers, bless you, first, minus these numbers second. Okay, you can't just do these minus those. You'll get a different answer. So if I'm doing B minus A, I've got, and I'm looking at their corresponding entries. Here's my row 1, column 1 entries. B minus A, does that mean 3 minus 5 or 5 minus 3? 5 minus 3, right? Not, whatever that is my upper left entry on my answer matrix. 7 here corresponds to what here? 2, which order am I subtracting? 2 minus 7. And then I have 1 minus, be careful about this. 1 minus, what corresponds to that over here? Negative 2. What happens if I have minus negative? Plus plus, right? That will be whenever you encounter that minus negatives, be sure you have your whatever I'm trying to say is on, because you need to notice that. You finish your math, I'm going to finish my math. When you're done, check your math with my math. Actually, let me check that my math is good. My math is good. And then do C. You know, I'm not going to do this detail every time. I just wanted to show this to you once at least, so you see the detail. But the rest, you can do it in your head, or show me some arrows or something, because otherwise it'll just end up being so much writing all the time. Raise your hand when you have C done, please. Thank you. Thank you. Thank you. I got this. Did you get this? 8, 9, negative 1, 7, negative 1, 6. Okay. Congratulations. You know how to add and subtract matrices. We are going to talk about... Excuse me, I'm sorry. Sorry, I can't easily turn the microphone off, so then I just have to sneeze in my microphone. Apologize. Okay. Monday we'll talk about matrix times a matrix, which works way different than this scalar multiplication. Scalar is just a word for a constant. So when I say we're doing scalar multiplication, I'm really just saying we're taking some number and multiplying it by a matrix. So this notation right here, some number k times matrix A, means you take every individual entry, that A sub ij, take every individual entry and multiply it by that constant. It's kind of like a distributive property. It's not, so I'm going to put that in air quotes. Kind of like the distributive property. It technically isn't, but it helps make the point. So in this example here, we have these two matrices up top. A is asking me to take 1/2 of capital A. What does that capital A stand for? All of the matrix, right? All of matrix A. So we're going to do 1/2 of every single thing in here. Mondo, come do this for us, please. You can take 1/2 of everything in that matrix and put your answer in right there. Yeah, that's right. All right, thank you, perfect. Who got that? When you took 1/2 of everything in matrix A. Thank you, sir. All right, so now we come to this last problem is our I will statement. 2 times capital A, what is that telling me to do? 2 times everything in there, minus 3B. This could be done a couple different ways. What do you think? There's 2 different ways that I could approach this negative 3B. Multiply everything by negative 3, or multiply everything by 3 and then subtract. You can do whichever one you like, but I have a warning for you. A lot of times when students try to go multiply everything in there by negative 3, they do that math fine, but then they go and they subtract it from what they got from 2A. Why don't you want to do that? Because you already took care of the negative. If you're distributing a negative 3 to B, then all you have to do is add that to whatever you get to 2A, because you've already taken care of the negative. What I'm going to do, because I feel like that's a subtraction, I like to do 2 times everything in A, 3 times everything in B, and then subtract those from each other. Before I even get there, though, before I even do one bit of math, what am I supposed to be checking? The same size or order. Do they have the same order? Yeah, they do. And the reason why I always check that, because so you don't go do a whole bunch of math and then finally go to subtract and be like, I can't do that. I did all that problem. Anyway, do your math. You do your math. I'm going to do my math. Don't look at my math till you're done with your math. So you can't unsee what you've seen.